we present AGIPC, a novel adaptive in-solve algebraic coarsening framework for GPU-based incremental potential contact.
Instead of explicitly modifying the mesh topology, which is expensive and disrupts GPU memory locality, we propose to perform coarsening purely at the algebraic level. Our method dynamically reduces the degrees of freedom within the Newton solve by aggregating vertices into supernodes, effectively constructing a subspace via a Galerkin projection. The pipeline starts with a parallel edge tagging process. Edges are classified as either collapsible or protected based on the local deformation state. Collapsible vertices are then grouped using a warp-level hash mapping scheme. This allows us to assemble the coarse system matrix entirely in parallel, without race conditions. This is how to decide which edges to protect from collapse. To govern adaptivity, we utilize the green strain increment as our error metric. If the strain increment in any element adjacent to an edge exceeds a threshold, that edge is tagged protected. Otherwise, it remains collapsible. Because deformation states evolve significantly even within a single Newton step, we reevaluate our criterion per iteration to maintain simulation fidelity. A major challenge in algebraic coarsening is artificial stiffness, which locks out rotational motion. We solve this with affine embedding. For supernodes representing significant geometry, we assign 12 degrees of freedom, capturing translation, rotation, scaling, and shearing. This preserves physical richness even at very coarse resolutions. After solving the reduced system, the solution is prolonged back to the fine mesh, followed by PCG smoothing to remove high-frequency errors. Crucially, we then evaluate contact barriers on the full mesh and assemble their Hessians into the fine system, strictly guaranteeing non-penetration.
We evaluate our method against stiff GIPC, the state-of-the-art GPU solver. Across benchmarks with 62K DOFs, we achieve speedups ranging from 1.8 to 3.3 times. Compared to traditional geometric multigrids, the advantage is even more drastic. Our method is over 7.5 times faster, as fixed geometric hierarchy lacks the adaptivity needed to account for different deformation. Even against algebraic solvers like AMGX, we demonstrate superior performance by avoiding the high construction costs associated with classical algebraic multigrid. In this twisting mat example with a Young's modulus of 10 to the 7th, our solver maintains robust convergence where traditional methods struggle. Furthermore, our algebraic approach scales efficiently with mesh resolution, showing a much flatter growth in computation time compared to full resolution solvers. We also shows the visualization of adaptive coarsening under different time step sizes. Smaller time steps lead to more aggressive coarsening on average, while our method remains effective even for relatively large time steps. Let's look at the performance across different benchmarks. In the multi-body squishy ball scenario, we achieve a consistent 3.2x speedup over stiff GIPC. For the dolphin example involving soft tissue deformation, our method maintains high fidelity while reducing the computation time. Notably, our framework is highly versatile and compatible with hybrid representations. In this Christmas scene, we demonstrate the seamless coupling with affine body dynamics, or ABD. The falling snowflakes are simulated as rigid bodies using ABD, while the rest of the scene is modeled with FEM. This is the visualization of adaptive coarsening of all Newton iterations in one time step. This proves that our method can be easily integrated into existing physics pipelines without sacrificing generality. In summary, we propose a topology-invariant, GPU-friendly algebraic adaptive coarsening framework. Our method bridges the gap between high-fidelity simulation and interactive performance. Thank you for watching.